Okay, it's time we take a look at some of the past paper questions, right? In the previous three videos, we look at tree diagrams on dependent and independent events. Now, in this video, we try to combine all the skills together and how do we, apply that skills to handle some of the DSE questions. All right. So this is an MC question. We have 6 numbers: 7, 8, 8, 9, 9, and 9. All right. So John draws one ball at random from the box without replacement. Alright, now this is a very important keyword, without replacement, until the number 9 is drawn. Alright, so if you draw an 8, you carry on. You draw a 7, you carry on. You draw a 9, you stop. Alright, so find the probability that he needs exactly 3 draws. Alright, now several things. Now, first, number 1, with or without replacement. With replacement means that you pick it up and put it back again. Without replacement means that you pick it up, throw it away, all right, and not to be, not to replace it literally. So what does that mean? If you do it with replacement, this is independent event, all right? We talk about dependent and independent, right? Because when you do it with replacement, every time you put it back, that means the original box is the same. So whether you take an 8, you take a 7, it has no effect because that 8, the 7 was put again back into the box. But when you do it without replacement, it is a dependent event. Because what you had taken out, if you took a 7, then in the second stage, there will be no more 7. Alright. If you pick an 8, then in the second stage, there used to be 2 8s to choose from. But if you take an 8 and not replacing it, then in the second stage, you have 1 fewer 8, number 8. You got only 1 number 8, alright? So when you do it with replacement, it is independent. When you do it without replacement, it is dependent, alright? There is also a similar case when you pick the numbers at the same time. When you pick the numbers at the same time, it is just like without replacement. Alright, remember that. If you pick the things at the same time, it is also dependent events, alright? Be very careful on how to distinguish between dependent and independent situations, alright? So in part 1 and part 3, we talk about the difference between dependent and independent situations, alright? This is number 1. Now, the second thing about this particular question is that now it seems that there are numbers 7, 8, and 9. But since the question only concerns whether the number is a 9 or it is not a 9, alright? So in fact, it would be easier if you look at that, instead of the box having 3 numbers, 7, 8, and 9, right, in different quantities. But no, you can imagine the box got only 2 things. 3 of them are 9. 3 of them are not 9. Alright, never mind whether they are 7 or 8, I don't care. Alright, all I care is that some of them they are 9 and some of them they are not 9. Alright, so we have 6 balls. 3 of them they are not 9. Never mind they are 7 or 8, and 3 of them they are 9. Alright, we can think about it like this. Alright, sometimes we can group some of the so-called different items together and just consider them as the same thing. Alright, so now if you need exactly 3 draws, right, we can pick a tree diagram. Alright, it can be a 9, it can be a not a 9. Alright, this is the first draw. And then you have the second draw, and then you have the third draw, alright? It can be a 9, it can be not a 9, alright? So it can be not a 9, it can be a 9. Alright, now but mind you, the game stops when you draw the 9, right? So if you draw a 9, the game stops here. No more branchings from here, right? But if you do not draw the 9 on this branch, you carry on the game, alright? So in order to have exactly 3 draws, the thing will be here, alright? This is where you have exactly 3 draws. Right, the game carries on from this branch, right? Do we have a game carry on from this branch and so on, alright? But the game will stop when you draw the 9 here or when you draw the 9 here, alright? So in other words, this red event is what we want, alright? In other words, we have the first one is not a 9, right? The second one is not a 9, but the third one is a 9, alright? And the probability will be that of these branches The first one is not a 9, is 3 out of 6. Alright, 3 out of 6. Now the second one, because there is one fewer, you take away one of them. Alright, so it goes down to 2 out of 5. And then 3 out of 5 for this branch. Alright, and then finally, 2 of the non-9s, they are gone. So it goes to 1 over 4 and 3 over 4. Alright, so after all, it is 3 over 6 times 2 over 5 times 3 over 4. Alright, that is the answer. And the answer goes to 3 over 20. Alright, so the answer is D. Okay. If you are good at it, you don't really have to draw the tree diagram. Like I said in the third part, you can just look at this. You think about it well. To let the game stop at the third draw, the first one is not a 9, the second one is not a 9, yet the third one is a 9. Alright, so you can only think about this branch instead of the whole thing. Alright, this is the branch that we are interested in. Alright, so never mind the others, Just focus on this one single branch. Alright, but if you want a complete picture, you can draw the tree diagram like I just did. But what I want to emphasize is that it is only an MC question. You have less than 2 minutes to do that. I think eventually you can develop the skill of not drawing the tree diagram, but thinking in terms of the tree diagram is important. Alright, anyway, so that would be this MC question. Okay? Well, then let's move on to the next question. Okay. So this is yet another MC question. We have 2 numbers, alright, taken from 1, 1, 1, 2, 2, 3, and 4. Alright. Find the probability that the sum of the number is a 5. Alright, so what are the sum that will give you a number 5? Alright. Probability that the sum equals to 5. Alright. So there are 2 ways you can get a 5. You can have 1 plus 4, you have a 5. Alright. And then 2 plus 3, you have a 5. And that's it. Alright. Or maybe 2 plus 2, no, 2 plus 2, no, 3 plus 4, no. Alright. These are the only 2 ways that you can give you a 5. So it is a 1 and a 4. Or it is a 2 and a 3. Alright. Or we use addition and we use multiplication. So the probability for 1 will be 3 out of 3 out of 7. Alright. To get a 1 will be 3 out of 7. Alright. And then after you take away the 1, there is only 1 out of 6 for the next number 4. Right? Because you take away the number 1, so that is 1 fewer number. So it goes down to 1 out of 6 for the number 4. Alright? And then we have the probability of 2 and 3. 2 and 3 will be, to get a 2, it is 2 out of 7. Right? There are 2, number 2. So the probability getting a 2 is 2 out of 7. Now that one of the 2 is gone, that is because they are independent. Oh, did I emphasize that they are taken at the same time? Alright. Sorry, I did not mention it earlier. At the same time. At the same time means they are dependent. Alright. At the same time means without replacement. Alright. At the same time means without replacement. So at the same time, without replacement. So we have, if you take away the 2, then there will be 1 fewer number to choose from. So that would be 1 out of 6 for the number 3. Alright, now can you match all these probabilities one by one? Alright, so at the end, the answer will be 3 plus 2 is 5 over 42, right? Am I right? Now, but wait, 5 out of 42 is not the correct answer. It's not the correct answer. If you recall what we did in part 2, we said that some of the branches, they have to repeat, right? Remember this. Some of the branches, they have repeat. And I made this mistake because I didn't draw the tree diagram. If I had drawn the tree diagram, I will notice that, well, the first number can be a 1, alright, 2, 3, 4. If I drew a 1 and then I drew a 4, then the sum will be 5, right? That is the case, correct? No problem. That would be this one, okay? But then if I had drawn the tree diagram, I will find that, well, there is another possibility. you draw the 4 first and then you follow by the 1, it is also a 5. Alright, so instead of 1 and 4, you have yet another possibility of 4 and 1. Alright, and then likewise you have another possibility of 3 and 2. Alright, if the answer is 5 out of 42, then perhaps you missed these. Alright, but once again, if you pay attention to it, you discover that, oh, the probability of 1 and 4 is just the same as the probability of 4 and 1. Alright, the blue one here is just the same as the blue one here. Alright, and similarly, the purple one here is just the same as the purple one here, right? Do you discover that getting the 4 is 1 over 7, alright? After you take away the 4, to get a 1 is 3 out of 6. These two blue terms, they are the same, isn't it? So likewise, this purple term will be the same. I'm not going to repeat this one. Alright, this purple term is going to be the same. In other words, you can just multiply this number to 2. Alright, now this number 2, this blue number 2 has the same effect, has the same origin of all these blue numbers in the video part 2. Alright, all these blue numbers. These are the number of times those branches are repeated, right? In this case, the branch 1, 4 repeats as 4, 1. The branch 2, 3 repeats as 3, 2. Alright, so you should have multiplied those by 2. And the answer goes to 10 out of 42, and that simplifies to 5 out of 21. This is the correct answer, not 5 out of 42. Alright, because the branch 1, 4 is going to repeat itself. Alright, it's so easy to make this mistake because you didn't draw the tree diagram. Alright, but I'm not saying that you have to draw the tree diagram. I'm saying that you have to be mindful. You have to be very careful to think about sometimes the branches they repeat. Right? How many times those branches they are going to repeat? That is usually the crucial part in the probability question, especially for those that that has a complicated tree diagram that is prohibitive to be shown. Okay.